All right, so we're going to do section 5.3 today, and that's all about doing the SOHCAHTOA, the trig ratios, in the coordinate system now, though. So looking at them in a coordinate system, so not just as a two-dimensional drawing, but that they actually have direction and distance. So we're going to talk about what that picture looks like, and then how we can use everything that we've done before, all of the SOHCAHTOA ratios, in a new application that way. So just remember what trig ratios actually are. Remember, they're just a ratio or a comparison of two sides of a right triangle. So if I give you a trig ratio, you know two sides of a right triangle, we can always find the third. Okay, so how do we draw these things in the coordinate system? I want you to go ahead and draw an angle in standard position, so meaning positive x-axis. And I'm just going to draw one that's a positive angle, and I'm going to draw the terminal side in quadrant 1 just so we have an easy picture to look at. So just go ahead and draw yourself any angle in quadrant 1, standard position. So that means we're going counterclockwise. Terminal ray is that second ray in quadrant 1. All right, so I'm going to name it with the most unoriginal possible name for this. Our Greek letter, theta, is going to be our angle measurement. That would also be then the reference angle to the x-axis. Remember, reference angle is that shortest distance to the x, so between the terminal side and the x-axis. All right, so now I want you to pick any point that you want, any point at all on your terminal ray. Doesn't matter where. We're going to talk about why that doesn't matter. Anywhere that terminal ray, anywhere on that terminal ray, the angle measurement, that theta, will still be the same. So it doesn't matter where you pick your point. And we're going to be, again, totally unimaginative, call it P for point. And then that point, to get there, you need to know two things. You need to know the x value, the x part of that coordinate, and then the y to be able to get to that location. All right, now I want you to drop a perpendicular from your point down to the x-axis. Go ahead and make your perpendicular there. So that is the vertical distance from the point down to the x. Now, what we have is a triangle with our base on the x-axis, the height as that distance from the point, and then our hypotenuse is the distance from the origin out to the point. So let's talk about what we know about that triangle if we know where the point is. If we know the point is xy, what would the distance be, or the base of that triangle? It would have to be x, right? It's your horizontal distance. What would the height have to be? Well, that would have to be y. And then there's only one piece that I don't know, which is the hypotenuse, but I could figure it out because I know, if I know the point, I know x and y. So we're going to call that r. We're going to talk a lot more about why it's an r later on, but for right now, just think of it as a distance. It's the distance from the center out to a point on the ray, which is kind of like thinking about a circle. Like the radius of a circle is the distance from the center out to the circle. So very similar idea. We're going to talk about that more in chapter 6. So from the point out to from the origin out to the point, we call that r. So we could figure that out by using the Pythagorean theorem, because remember, you know the ordered pair, you know the x and the y. So we can just use the Pythagorean theorem. So that means r would be the square root of x squared plus y squared. So we can figure that out. It's pretty easy to do. Now, think about what that picture is then. Basically, what we know is by giving you an ordered pair, we gave you two sides of a right triangle. We're using the reference angle. So the distance to the x-axis, and then we can find that third side. You can do all of your SOHCAHTOA ratios then using x's, y's, and r's instead of the language we used before, which was adjacent, opposite, and hypotenuse. We can put it into the plane then, and we can have the idea of what direction would look like. So in quadrant 1, everything's positive. That's great. In quadrant 2, though, when you look at ordered pairs in quadrant 2, x is negative. So that's going to change some signs of our ratios. So we actually can have positive or negative trig ratios because we have that direction idea. In quadrant 3, they'd both be negative. And in quadrant 4, just the y is negative. So as we move from quadrant to quadrant, the positives and negatives change. So it's really important to keep track of where we're located. All right, so let's do that translation now. So when you think of that picture, I'm just going to redraw it here so we have something to talk about. So we have our theta, we have our y, this is our point up here, and our x, and then our r. When you think about those locations, we can write the trig ratios then for these, just thinking again that the x is adjacent, the y is the side that is opposite the angle, and the r is the hypotenuse. So in SOHCAHTOA, we can translate opposite, adjacent, and hypotenuse into x's, y's, and r's. So let's take a look and do that for sine. So the sine ratio is opposite over hypotenuse. So in our triangle, that would be y over r. So that means cosecant, because it's reciprocal, would be r over y. All right, cosine, it's adjacent over hypotenuse. So that would be x over r, which means for secant, we just flip, it would be r over x. Tangent, toa, opposite over adjacent. So in our lingo then, that would be y over x. And remember, what is y over x? When you see change in y over change in x, that's slope. So tangent is slope of a line. When we think about that ratio of y over x, it's the slope of that line. All right, now cotangent then would just be x over y, so reciprocal. Now, the one thing to keep in mind, and it's this little helpful hint down here, is because r is a distance, it is always going to be positive, no matter what x and y are doing. The radius, the r, distance from the origin, always a positive value. The only thing that can be negative are x's and y's as you move from quadrant to quadrant. And you know that, you've graphed tons of points, it works exactly the same as what you'd like it to. Okay, so what we're going to do is walk through 4 examples here that talk about basically how do you draw the picture and how do you write those ratios. So for the first one, it says find the values of all the trig functions for an angle in standard position if the point -15, -8 is on the terminal side. I started the picture for you, but I want to add a little bit to it. So standard position, just draw this with me. Put your vertex at the origin. Positive x-axis is your initial ray where it starts. That means they've measured an angle going around counterclockwise. And the terminal side, so if you can trace over that blue side with me. I know on your paper it doesn't look blue, but on the video it should here. So go ahead and trace out that terminal ray, extend it beyond where the point is. So that's the terminal ray of your angle. So that angle, that green angle that I just drew, is the one that they're talking about. Okay, so where does our triangle come from then? So they've selected the point -15, -8. They could have picked any point on that terminal ray, and the ratios are going to be the same, the angle is going to be the same. They may look a little bit different when you simplify them, but the decimal equivalent is going to be equal. They're similar triangles then. They would be proportional, so all of them have the same value. That's why it doesn't matter where you put the point on the terminal side, the proportion will be the same. So we can use whatever is easiest for us. So that's the point that they've picked. We need to drop the perpendicular to the x-axis, so you must always go back to the x-axis and then back over to the origin. So the triangle that we have always starts at the origin, goes out to the point, back to the x-axis, and then back to the origin. So we have that reference angle, distance to the x-axis is the theta that they're talking about. You cannot do the y. Otherwise, everybody's going to have different triangles. We're trying to make this standard so everybody's looking at the same thing. All right, another question for you to think about before we keep going. This idea of reference angle. We always use the reference angle. Think about coterminals. We talked about that in the previous sections. What does coterminal mean? Well, coterminal means it ends in the same location. So any triangle that is coterminal with this side R is going to have the same reference angle, which means instead of having infinitely many triangles to look at, if all we think about is just the reference angle for all of those, they all become the same triangle. The terminal sides are the same, so we're always drawing the same picture, which makes it a whole lot easier to look at. Okay, so let's list what we know. So our x value is -15. Our y value is -8, so we know those two legs of the triangle that make up the base and the height. The part that we're missing is the r, so go ahead and solve for r. So r squared would be -8 squared plus -15 squared. And I think this one works out really well, but pause the video for a second, figure out that number. Take the square root, and what'd you come up with? So hopefully, coming up with 17. So that means we have a nice Pythagorean triple. It's so much more fun to work with, I guess, if this can be fun, to be able to have a number that's not a radical. So positive number again, remember, because it's the distance from the origin out to the point, it's always going to be positive. Okay, so let's write our ratio. So let's start with sine and go through the different values here. So sine is equal to y over r in these labels. But remember, the y and the r, that's still thinking about opposite, hypotenuse, adjacent. So if it's easier for you to put those words in, because remember you're always using the angle up here, the reference angle. So the side opposite, the adjacent, the hypotenuse, this is the same thing. We're just calling it y and r and x now instead, because it's the same idea. So opposite over hypotenuse, or y over r, would be -8 over 17. So we're using opposite and hypotenuse. Can't simplify it, good to go. Cosecant, I'll just do that one right away, then would be r over y. So that would be 17 over -8. Now, does it make sense that sine is negative in quadrant 3? Well, y's are always negative in quadrant 3. The r's are always going to be positive, so they're always going to be opposite in sign. One's plus, one's minus. Always going to be negative then. All right, well, what happens with cosine? Same idea. X over r. The x value is negative 15. That's the adjacent side over hypotenuse, or the r. Going to be negative again because you have one of each. And secant, same deal. When you flip something, it still has the same sign as the original fraction. It's just the numerator and denominator switch because it's 1 divided by, also going to be negative. All right, let's do tangent. So the tangent value for this one, tangent, y over x, the slope of that line. Let's think about this. So we're going to be taking y, which is negative 8, over x, which is negative 15. Now think about that for a second. A negative divided by a negative, going to have to be a positive. So it'd be 8/15. Think about if that is reasonable to you. Look at the terminal side. Does that have a positive slope? Well, for sure, going up 8 over 15, up 8 over 15. But remember, when you can count slope, you could also go down 8, left 15, which is the negative and the negative. But definitely it needs to end up to be a positive number. So will all tangents be positive in quadrant 3? Well, sure, because your x and y's will always both be negative. So it's always going to be a positive answer. So in quadrant 3, tangent is always going to be positive. What other quadrant will tangent always be positive? Well, also in quadrant 1, because they'd both be positive. What would happen in quadrant 2 and 4 for tangent? Well, in 2 and 4, you're going to have one of each side, x and y, so they're going to be negative. So I want you to start looking for those patterns in those numbers. Think about what should be true. So cotangent, we just flipped. So that one, the picture was sort of started for you, but you need to figure out what the reference angle is, what that picture looks like, and that third side. All right, so let's try one kind of from the beginning. It says you're going to have another angle in standard position. The terminal ray includes the point negative 6, 9. All right, so standard position again. So we're starting at the positive x-axis. We're measuring an angle into quadrant 2. Now, how do I know how far to go? Well, for this one, they actually gave me the location, so I'm going to go ahead and graph the point. 1, 2, 3, 4, 5, 6, negative 6. 1, 2, 3, 4, 5, 6, 7, 8, 9. And I'm going to graph that point. For me, it's a lot easier to put the ray in when I know where the point's going to be first. So it means then that the terminal side starts at the origin and goes through the point negative 6, 9. Would have been super awesome if mine did. So there's the point that it goes through. So negative 6, 9 is on the terminal ray. Again, they could have picked anything on the terminal ray. These ratios would all end up being equivalent because they're similar triangles. It works the same way. All right, so drop the perpendicular down to the x-axis, back over to the origin. So this is the triangle that they're talking about. The reference angle, so the distance from the terminal side to the x-axis, is your theta that they're talking about. It's always to the x. So important. Reference angle, we're always measuring the same way. So the hypotenuse is from the origin out to the point. All right, so let's put in what we know. The x is negative 6. I know that seems weird to have a negative, but it's the direction. The length of the side is 6, but the direction it's traveling is in the negative direction. The hypotenuse, or the y value is 9. I don't know the hypotenuse or the r, so let's find that first. So go ahead, pause the video for a second, figure out what your hypotenuse is. Okay, so I got a 117, which is kind of a suspicious number. It kind of seems like it might be a whole number, but it's not. Alrighty, so let's see if we can figure out what that would be. So 3 square root of 13. Now let's talk plus or minus for a second. Do we need plus or minus for that side? Well, it's the radius, so the answer is no, because it's the distance from the origin to the point, always positive. So I know that that one's going to be positive. Now I have everything I need. I can go ahead and write those ratios for quadrant 2. So sine is equal to y over r. In that triangle, again, sometimes people like to just to list the information. X is negative 6, y is 9. R is 3 root 13. Like if it's easier for you just to identify it from like a list of information as opposed to thinking, okay, opposite over hypotenuse. I mean, whatever is easiest for you. Put in the words if that's helpful. But they're still exactly the same ratios. We haven't changed that. So y is 9, hypotenuse is 3 square root of 13. Reduce and rationalize. So we're going to do the same things we did last week. I'm going to go ahead and do cosecant right away then. R over y. Remember, we have a choice. We can flip the first one, the second one, or the third one. Easiest one to flip by far is that second one. All right, cosine x over r. It's the ratio of those two sides. For x over r, that would be negative 6 over 3 root 13. Simplify. And then, I'm going to move that. Rationalize. So negative 2 square root of 13 over 13. So that means secant would be r over x. Flip the middle one again, so much easier. Don't flip one that you've already rationalized. That's a lot of extra work. And then tangent. So tangent would be y over x. So in this triangle, that would be 9 over negative 6. So 3 over negative 2. Now just a quick reflection on that. Look at your terminal side. Does it make sense that that is negative slope? Well, for sure. You're going down and then to the right. That's negative slope. Cotangent, x over y, negative 6 over 9. Guess I could have just flipped the last one, but there you go. So negative 2/3. So think about this for a second. In quadrant 2, does it make sense that cosine is negative? Look at the green ones. Well, sure, cosine has to be negative because it uses the x value, right? If it uses the x value and the r, it's going to be negative in quadrant 2. So tangent, same deal. You have a y and an x. You have one positive, one negative. That's why it's negative in quadrant 2 as well. Okay, so those are pretty typical, I would say, triangle examples, things that have radicals, things that don't, how you draw those. So let's talk about a more unique situation. So take a look at where they want this point to go. They say the point, when this angle is in standard position, ends up to be 5, 0. 1, 2, 3, 4, 5, 0 on the x-axis. Okay, so let's think about what that means then. So the initial side of this triangle is the positive x-axis. But the terminal ray also ends up as the x-axis, the positive x-axis. So how could you have an angle measurement that ends up on the positive x-axis? Think about that for a second. Give me an example of an angle that would end up there. Well, how about 360? If you go all the way around the circle once, you'd end up right there. How about negative 360? All the way around the circle the other way? 720, 1080. You could keep going around and around. How about 0 degrees? What if you had 0? You didn't go anywhere. That's an angle. 0 is an angle. So you could end up there. So it's totally possible, and actually happens quite frequently, that you actually end up on an axis. So you could end up over at negative 50. So you could end up over here. That would be 180, negative 180, things like that. You could end up on the positive x or y axis. You could be at 90 degrees. That would just mean the x is 0. So you can definitely have angles that end up on the quadrants. We have to be able to deal with those too. The goofy thing is, it doesn't really look like a triangle anymore, does it? So think of it as a triangle whose height, so this height value, the y, keeps getting smaller and smaller and smaller until eventually it's just a line segment. So that height decreases, decreases, decreases until the terminal and initial ray is equal. Now I know that seems odd, but it's totally legitimate in our coordinate thinking to have an y value that's 0. Our x is 5 and y is 0. So what happens? Can we still find r? Well, sure. R is just the distance from the origin. So how far is 5, 0 from the origin? Well, it's 5. You can just count. It's the same as the x, but you could still do this, right? You could still do your Pythagorean theorem. 5 squared plus 0 squared equals r squared, and you'll still get r equals 5. So we can still do this. I know it seems weird. There's no triangle, but there's definitely still an x, a y, and an r. So let's see what happens with the ratios when you do that. So for sine, for y over r, you get 0 over 5, which is 0. In other words, the height change is 0, so the sine would be 0. So sine at 0 degrees or 360, any of those values would be 0. But look what happens for cosecant then. If you do the reciprocal, that means you'd have 5 over 0. Is that a real number answer? Nope, that is undefined. So when we talk about that one, that is not a real number answer. So when we graph those, there's going to be breaks in the graph. You're going to see asymptotes. It is not a domain of anything you want for those reciprocals, because wherever sine is 0, its reciprocal will be undefined. Okay, let's look at what cosine does. X over r. That would be x is 5, r is 5. So that's 1. Now, let's talk about this idea of it doesn't matter where you put the point on the terminal side. What if my point was at 7, 0 instead, or 28, 0, or 100, 0? When you do x over r, the x and the r will always be equal, right? Because that's the distance away from the origin as well. So that ratio is always going to be 1. The ratios are always the same. So It doesn't matter where the point is on the terminal ray. The sine, cosine, tangent values are always going to be equal because those are similar. All right, so secant then, r over x, would still be 5 over 5, still be 1. So the reciprocal of a 1 is always a 1. Okay, let's talk about tangent. So tangent of that angle, y over x. Okay, think about slope. It's horizontal. What should the slope of a horizontal line be? Well, it should be 0, and let's see that is. So y is 0, x is 5, so we get 0. So think of it as a slope. It's horizontal, got to have a slope of 0. And whenever sine is 0, tangent's going to be 0 too. Can you see why that's going to be true? Look at the two ratios. So whenever sine is 0, tangent is 2. Look at what they both have on top. The y, and when y is 0, yep, the answers are going to be 0. Cotangent, when you flip, we have the same problem that when we flip sine. You end up with a 0 in the bottom, which is undefined. So just got to be careful there when we look at those. So domain won't always be all reals, but you can definitely still have angles on the axes. Okay, last question. This is really going to pull together what we talked about last week too. So go ahead and read through it. You can pause the video if you need to, read through it. I'm going to circle that pertinent information here. They're giving us that the cosecant of theta is equal to square root of 85 over 9. So I'm going to go back to the definition of a trig ratio. If I give you a trig ratio, it means you know what? Two sides of a right triangle. So if I'm giving you cosecant, it is the reciprocal for sine. So if all I had to do was find sine, I'd be able to do it right away because I would just flip this. I'd need to rationalize it ultimately, but I would just flip that. Sine is opposite over hypotenuse, which means this one has to be hypotenuse over opposite. So I gave you two sides of a right triangle. If I give you two, can you find the third? The one you're missing is adjacent. Well, sure you can, because you know the Pythagorean theorem. So let's go ahead and draw that. So it's in quadrant what? This super matters. Why does it matter what quadrant you're in? The signs, the positives and negatives, so make sure you know where you're going. All right, so we're going to draw an angle in standard position with its terminal ray in quadrant 2. So that's what they mean. Pick a point anywhere that you want to, kind of like your original picture, on your terminal ray. Drop the perpendicular down to the x-axis, over to the origin. So the origin out to the point is your hypotenuse, which they gave you because I gave you cosecant. So that's square root of 85. The side opposite, again, it's always the reference angle, so it's the angle between the terminal side and the x, is 9. The side you are missing is the x. Go ahead and solve for it. So x squared plus 9 squared equals square root of 85 squared. Go ahead, pause the video, solve for x. So we get x squared plus 81 equals 85. So x squared equals 4, square root. Okay, so here's the discussion we need to have now. X technically can either be positive or negative, right? Because when we square root and we're in the quadrants, x can be positive or negative. How do you know which one you're going to pick? Go back to this. When you're in quadrant 2, x has to be negative, right? Because it's the x value. We know we're going left. So in this case, I would want to pick the negative 2 as opposed to the positive. It depends on the quadrant. So the picture is really important. Okay, so let's go back and we're going to write all the other trig ratios that we know. Sine we'd already started because I know they gave me cosecant, so I could just flip it. The only thing to finish off sine is just go ahead and rationalize it. All right, let's do cosine. So cosine x over r would be negative 2 over the square root of 85. Can't simplify it, so just go ahead and rationalize. And then we've got secant is r over x then. So flip that first one. We didn't have to simplify it all, so we can go ahead and just flip it. So both of those would be negative because you're in quadrant 2. And then tangent. So tangent would be y over x, which would be 9 over negative 2. Negative slope again, that makes sense, going down to the right. And then cotangent would be x over y, so negative 2/9. So think about what positives and negatives those things have to be, but this is so critical, just realizing, hey, they gave me a trig ratio. What does that mean? I know two sides of a triangle. If they give you an ordered pair, hey, what does that mean? They gave you two sides to a triangle. If you know two, you know everything because you can draw it and find the third. So just being aware, now we have direction as well. So we have to think about what quadrant we're in to be able to deal with that. So trig ratios in the coordinate system. And then from here, we're going to be doing applications. So when we get to the next section, we'll talk about how can you apply this in real situations. 5-3.